Alright guys, the last part of this chapter, after having so much information and hopefully you have remembered lots of stuff from your general chemistry. Let's talk about electronegativity and polarity of bond and molecules at the end. You remember that in covalent bonds, the two atoms share the electrons between them. So some of the bonds are called non-polar covalent bonds, means that the tendency of the atoms to pull the electrons in the covalent bond, which is interpreted as electronegativity, it's almost the same between the two atoms. It's either the same, so there is no electronegativity difference like you see in CC, or the electronegativity difference, this tendency to pull the electrons, is very close to each other, like what happens between carbon and hydrogen bonds, or sulfur and hydrogen, or sulfur and carbon. So I would remember these non-polar bonds: carbon-carbon, carbon-hydrogen, sulfur-hydrogen, and sulfur-carbon. The rest of the bonds are going to be polar. So what are the polar covalent bonds? Carbon-oxygen single bond, carbon-oxygen double bond, carbon-nitrogen, carbon-chlorine, and nitrogen-hydrogen. So it means that the electronegativity is going to be different in these two atoms, between the two atoms. So, like for example, if you want to determine the polarity of this bond, you would say oxygen is more electronegative than carbon. The trend of electronegativity is increased from left to right across the period and from top to bottom. From bottom to top in a group. So oxygen is here, carbon is here, so oxygen is obviously more electronegative. Then we can assign the signs delta, lowercase delta, and negative, and call it the partially negative side of the molecule, and then oxygen induces partially positive sign on or charge on the carbon. So it means that if you look at this bond under the microscope, you will see it as like more density on oxygen. Then you can draw an arrow which is called dipole moments. It's always pointing at the negative center of the bond. This is what you already knew from general chemistry. So electronegativity difference causes the polarity of the bond, and you can draw a dipole moment for the bond. So now you can draw it for all of these bonds in on page 22. Like for carbon-hydrogen, what is the polarity of the bond? You just learned that carbon-hydrogen is nonpolar, so there is no polarity. I just call it nonpolar. But like between carbon and nitrogen, what would you say? Carbon and nitrogen, which one is more electronegative? It's one of the polar bonds, so it's more negative. Carbon over carbon is more positive. Or like for CX, X in organic chemistry is halogen, fluorine, chlorine, bromine, and iodine. So unlike math, X is completely known, and we know that there are the elements in group 70. Okay? Now, after knowing the polarity of bond, let's talk about the polarity of molecules. So let's elevate it to the molecular level. First, we need to determine, to draw a correct Lewis structure, then determine the polarity of each bond, and then decide on the polarity of the entire molecule. For a simple molecule like CH3Cl, after I draw this correct Lewis structure, I'll try to determine the polarity of each bond. We just learned that carbon-hydrogen bonds are non-polar, so we cannot put any partially positive or negative. You cannot determine the polarity, polarized sections. But how about between carbon and chlorine? Carbon and chlorine is a polar bond. Chlorine is more electronegative and carbon is less. So seems like polarity is towards chlorine. For a molecule like this, formaldehyde, Again, carbon-hydrogen bonds are nonpolar. The only polar bond here is carbon-oxygen. So it's partially positive, partially negative. That's how you determine the polarity. Some of the molecules don't have polarity, right? Like in simple hydrocarbons, only carbon-hydrogen. We just learned that carbon-hydrogen bonds are all nonpolar, 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 all of them are nonpolar, right? And also carbon-carbon is nonpolar. So the whole compound is nonpolar. Some of the compounds like carbon dioxide, if you draw it, the Lewis structure, you see that between carbon and oxygen, oxygen is more negative and carbon is more positive. But the electronegativity for oxygen is more than carbon. And it's like you have two vectors with the same strength, the opposite sides, so they cancel out each other. So it's a non-polar molecule. Or when you draw CCl4, the same. When you draw the vectors, they all cancel out each other. So it's another non-polar. Although the bonds are polar, carbon, chlorine, they are all polar. But because of the geometry of the molecule, all the vectors are going to cancel each other. Also, you can have like between, you will see these types of molecules more often later on. So you see between carbon and hydrogens, no polarity, no polarity. Between carbon and chlorine, polarity, polarity. And seems like both, because both of the chlorines on top seems like there is a big dipole moment in between the chlorine atoms here. So that's, you may ask me why this molecule looks like it. It's a geometrical isomers that you haven't learned yet, but you will get used to seeing them more often, and we will going to name them later. So let's say if just we switch these two chlorine and hydrogens with each other, you saw this is polar, and this molecule, carbon is partially positive, chlorine partially negative, the same on carbon and chlorine. So seems like carbon hydrogens are nonpolar. So between carbon and chlorine, you see again the two vectors, the same length, opposite sides, so they cancel out each other and they make the molecule non-polar. So now you can determine the polarity of each molecule. And why did we learn this? Because we need to determine the polarity of some organic molecules. Later on you will learn more about functional groups. I'm sure you had them in General Chemistry 1, but let's see. Nicotine molecule, we all know nicotine exists in the main ingredient of cigarettes, right? So if you want to find the polar and non-polar sides of this molecule, a nitrogen carbon bond is polar, right? I just put P. The rest of the molecule, all carbon, 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 hydrogen, they're all non-polar. I show it with NP, okay? Polar, non-polar. Or when you want it for, let's say, penicillin. All right, so any carbon hydrogen combination is nonpolar. Carbon oxygen is polar. Carbon nitrogen is polar. We don't have to be specifically on each bond, but just the area. Carbon oxygen double bond is polar again. Carbon nitrogen is polar. But carbon sulfur, if you remember, it's nonpolar. And finally, carbon oxygen is polar. So we just go with the same principles of polarity of the bonds. So you can work on the rest of these compounds. Another practice you have on page 24 is we're supposed to, let's get rid of it. Trying to decide between page 24 and 25, see which one is better to work on. Let's work on page 24. A compound is given, L-dopa, which is used to treat the Parkinson's disease. Okay, so we are supposed to convert this skeletal structure to a Lewis structure. So we have the ring. Don't forget about double bonds. Then hydrogens we have. CH2 here, right? This is a CH2. CO and OH. Let's see what is the next task. What is the hybridization and geometry around each labeled atom? The first labeled atom is this. You remember, for the hybridization, you do not count the pi bond, only sigma bonds and non-bonding electron pairs. How many sigma bonds do you have? 3. So the first one is S, and how many more do you have for P? 2. So the hybrid is sp2, because there is no non-bonding electrons, so it's trigonal planar. It's a flat molecule. The rings with double bonds are all flat. The second carbon has 1, 2, 3, 4 sigma bonds. So 4 sigma bonds. The first one is S and 3p. So it's sp3 with no non-bonding electrons. So it's tetrahedral. For nitrogen, don't forget I told you after 3 bonds connected to nitrogen, the last one is going to be non-bonding electron pairs. So you have 2 hydrogens, if you want to open the hydrogens to understand it better. You have 1, 2, 3, and the fourth one is a non-bonding electron pair. Again, 4 total. So the hybrid is going to be sp3. Because there is a non-bonding electron pair, the difference between this sp3 and this sp3 is that the shape. So this is going to be trigonal pyramidal. Trigonal pyramidal. Okay, and label 3 polar bonds. Excuse me. Let's label the 3 polar bonds here. So you just look for the atoms with the electronegativity difference. So can I say this is a polar bond? Of course, you can call it a polar bond also. What else can we call a polar bond? Carbon, nitrogen, right? I should have put it as, I forgot. This is a carbon, right? And it does not have any hydrogen. So this is a polar bond also. And these bonds are polar. So you can easily label more than 3 polar regions. Okay, on page 25, you have a similar practice. Don't forget to work on the end of chapter problems, and let me know if you still have any question about the study guide.